So this project is a regression problem, and we are going to go from start of the project from downloading the data all the way to developing a regression model and save in the form of pickle file so that it can be used for future predictions. So this problem, unlike the one that we have seen before, like Titanic, it's not a competition where we the data is not from a competition, but it was from a census data, and it was purely derived from there is a from a textbook, uh, which is hands-on ML learning, and there is an end-to-end problem. I took the same data set and followed more or less the similar analysis um, to develop this pipeline. And if you go to uh, GitHub, you could see their package. But let's start with what we are trying to do here. So as usual, I'm setting up a configurations where I have various folders. Um, for example, I have a utils folder which has some utility functions so that I'm importing. So I'm using this particular code to import. For this notebook, wherever I'm using utility functions, I'm copying that particular code within this notebook so that it's complete. But if you are using certain functions over and over, it's better to put into some Python classes and then call them and you reuse them. Right, so this is my project structure. There's a project directory, and within that there's a data folder, notebooks folder, and images folder, and this is the name of the project. So within this one, I am going to download this particular file. In fact, this is the data that I am going to download and extract into my data folder, this housing.csv. So this is a path for that particular file, and then this particular code will open a housing.tz file which is located this at housing, this URL, and then we retrieve it and we are going to uh, extract it and save it in this data directory. That's what this code does. And then finally, if you want to load this particular file, all we have to say is load housing data, and it will load this particular file into our bd.csv. So these are useful pieces of code if you are trying to extract from a URL. So what is this data set? So this data set, the description is given here. It's essentially collects California data. It's from 1990 census. It is collecting housing information on a block, and each block is divided by this latitude and longitude. So if you want to see this one, so this is a California map, and you can see that each of these dots represent a California map block, and each of these or we collect data on this block, and there are several of those blocks, and there is something known as medium household value, and we are trying to derive it. Although the data set provides everything, we are framing using this data to frame a regression problem to derive that. Let's go through this one. So if you look at this, what we have in this data, the data is has about 20,640 rows, and these are the values in it: longitude, latitude, median age, total number of rooms, total bedrooms, total population, um, median income, household value, and ocean proximity. So you can see this is the latitude and longitude. So each block, and this is the median age of the house, and the total number of rooms in the whole block, and the total number of bedrooms in the whole block, and the population within that block, and number of households in the block, and income. This is expressed, I think you need to multiply by 10,000. So this is expressed in 10k, so it's probably like 72,000, and then this is the household value, and then it says whether or not it's in the near the coastline, right? You remember this is the coastline, and then these are the blocks, and it is saying whether it's closer to sea or not. So whenever a new data set is given, we are displaying that particular CSV file, and then we are also printing the information file that gives us what are all the columns that are there, and also the memory that's using in this particular laptop, like 1.6 MB, which is not a lot. And then you can we can summarize the by column. So that can be done here. So each column is there, and then what is the data type for that particular problem? The ocean proximity is the object. Everything else is a floating point value, latitude, longitude, and we could probably convert them to optimize, but I don't see a necessity here. And total number of bedrooms within a, there are some records that are missing, so maybe we have to impute. And in the future data set, let's say somebody is submitting similar data set, other attributes can also be missing. But for now, this one, about 1% of the data is missing for total bedrooms, and you can see different values here and the number of unique values here. Since it's a real values, we don't really care about how many unique, but for the category 1 we can see that there is a 5 unique values. So again, if you do a describe, you can actually see various metrics, the number of the count and the mean, standard deviation for each of those uh, real values. Once you are done looking at it, there are some observations that you could make. For example, uh, there is always some caps, maximum value. For example, for certain places it is capped at, like for example this one is capped, looks like it's capped, and looks like this also capped, but a visualization is probably better for understanding this kind of capping and also understanding the data. So we can do some visualization, and I wrote this plot function to do visualization, and I can show you the code, and that code is plot variables. So it's essentially taking the variables to plot, and if there is a continuous variables, then it will try to do a histogram and number of columns and rows, and this is the code that it uses to plot uh, the variables that we have here. So now if you can see the longitude, latitude, income, and so on. As you can see, this particular value, the median age, it seems like it is capped at certain point. So everything that is older than 50 years, it is put into the bucket of this 50 51. Let's say maximum of median age, this is the 52, and you see that the 52 is represented a lot of time, that means it's the cap. So also there could be other caps, like for example here there looks like there is one value here while there are no values here, and so on. So seems like there are caps. So then also the frequency of how far uh, the houses are from the sea. Next, if you want to look at latitude and longitude, this represent like a California map that we have seen. This one is plotting a scatter plot to do latitude and longitude. But to make it a little bit more informative, we can use our attributes. For example, here the same plot is plotted with some transparency, and also the size of the bubble um, it can be computed by the population, and you're dividing by 100, so it gives some value to plot here. And then the label, median household value, the color, and then it shows the color bar as well. So to draw a scatter plot with additional details, it is much more informative, and in fact you can lay it out on top of the California map, and that's where you generate this kind of map. And you can look at the code at end-to-end machine learning here. So these are the, again, to understand how our variables are related to the response variable. In this case, the response variable is median household. So I fitted each of the variable on the x-axis, for example, longitude, against the median household value, and then the equation is here. So you can see that you don't really see a lot of significance for these, but a couple of them are important, like total rooms, like, and median household value. Makes sense because they are directly related, and also median income and household value, house value, right? So if you're earning more, you'll probably buy a better house. So this also makes sense. um, yeah, so and after doing that, we can look at certain correlation. Which of these other values, like you can look at the correlation between median house value against all other variables. You can see that all of these variables, the correlation is highest for median income, and then median age, and there is also negative correlation for latitude. Maybe it's going away from the sea, not sure, but that's what happening. So we can do some feature engineerings, compute rooms per household within that block, average, right, rooms per household, and then number of household by total number of rooms, number of bedrooms by total number of rooms. So bedrooms per the number of rooms available, and then population per household. So if you plot, after engineering, if you plot these, you will see that the bedrooms per room is an indicator, negatively indicating the price of it. So, so, we did find some important variable after feature engineering. So maybe we can use this to fit uh, into our regression equation. We're going to look at a pipeline building. So for numerical variables, we can impute the numerical variables whenever there is missing. We can add additional features, right? So we looked at these three ratios, and we added to the to the existing, like, trained EF here. We can do the same thing, and also we can scale it, scale the values, and optionally, if any of these bars need to be transformed into normalized values, then we can use log transform. So if it's optional, but we can technically do it. For categorical variable, we will impute each of those values using measure class, and then we can do one hot encoding. For the model, we can evaluate various models, but maybe the final model we're going to look at here is random forest regressor. Let's explore how do we even build. So we will look at various transformers individually. So for example, if you can have a simple imputer, right? So, and then there is a standard scalar. These two can be applied depending on the strategy. You can apply a numerical or categorical variable. Standard variable is definitely numerical variable. One hot encoding is a categorical variable, and these two imports are needed to write our custom transformer. So let's one of the things that I noticed when I was trying to write our custom transformer is that if you look at this particular code, for example, this is a code to write uh, add additional variables, ratio variables, the ones that we have seen in our these ones. So these were not existing in our data set. So we want to add these variables by computing these ratios. So this the same task I wanted to do, and I started writing this code. So what I was trying to do was, so I was passing the column names and then the ratios. So then here I did, so this is how I passed the ratios in, and then I computed these variables, and then I'm returning that particular variable data frame back. But I realized that most of these transformers or numerical variables actually work on numpy array. They don't have column values. So while it is useful on its own to generate a transform data, this it in a pipeline you're using, for example here imputer followed by this custom variables, and then you are scaling it, right? So but this scalar and imputer, they require numerical values, or it works on numpy array, but this particular program is giving me back a data frame. That's how I coded it, right? So but this is not very efficient. So the better way is to do is to actually generate a transformer in the form of a numpy array. So even if I pass data frame, for example here in the transform code, I'm checking if it's a data frame. If it's a data frame, I'm deriving the values, and then I am applying these three transformation, and appending to the existing numpy array these variables, right? So we don't actually know the column names where once this is done. So this is how to write a custom code. So and then here is where I'm computing hash indices, where the first value is column name and the second value is the indices. So if you look at here, I'm saying total rooms. So because it's a numpy array, it works on indices. So this hash table will have the indices per particular row. So I was a little bit worried when writing this code, because because you're adding variables, removing. If it's a pipeline is too large, maybe the columns will be shifted. Also we are dropping certain variables. It's also possible. So it was a little bit tricky. I wanted to avoid, but I could not, and we have to add these variables. So I just the only coding that was done was here. So hopefully this doesn't mess up anything in computing this. So for example, if you want to use imputer, right? So let's say how we define imputer. We said imputer is simple imputer strategy is equal to median. So if you want to write, the way to work on this is imputer result is equal to imputer fit transform, and give a numerical feature to it. That way it will impute the missing values. Same thing if you want to do one hot encoding, you fit transform one hot encoding features, and you are providing categorical features, and you are then so in the previous example of we noticed that we are passing a numpy array. So that's why we are constructing a data frame here. Even here, the result of this transformation is a numpy array. So we are getting this result and also adding these column names, which are available in our features names.out. So then we can print this. So I did print this. So you can see the results here. So when you do the imputation using, you get a numpy array, and in order to add columns and data frames, I extracted the column names from before, and then create a data frame, and you can see this is the data frame, right? And then you have one hot encoded. Once the data frame is created is here, so on, right? So and again I tested the attributes here, the first one, which will actually give you a data frame, as I told you. So these are additional columns that were created, but this is not efficient because the pipeline actually, numerical pipeline actually works on numpy array, so we will be missing some values. So instead I also did this append ratio variables too, and that code is when you actually do it, it generates numpy array. But to create a data frame, I had to append all the columns. So first, because we are applying fit transform the housing, so these are all the columns that are needed. but we also created these three additional columns in the function. So we need to create all attributes as the column, and then I created a data frame. So in this particular block I'm showing individually, but we will look at how to combine them together, right? So this is the function that we just looked at, and then these are the hash indices. So numerical pipeline, how are we building? We are doing three functions. One is imputing, and then we are adding attributors, and then we are doing a scalar. So this is the numerical pipeline, and this is the categorical pipeline. You're first imputing with the most frequent value, and then doing a one hot encoding. So once you have these two, we are creating a transformer. These are pipelines, and this is a transformer. Within the transformer, we are saying this is a numerical pipeline, and it should be applied with numerical features too. This numerical features too, if you look at it, this one it doesn't have numerical features, but doesn't have uh, the response variable, which is housing median value. And the categorical features we are applying this cat pipeline. So this finally the data processor pipeline. This will process all our predictor data, and it can be encapsulated in this way. So here I am applying only numerical pipeline, and I can show you the result, but on this one, and then I'm displaying df2, but the whole data pipeline, and I am adding the extra values and categorical values. This is how you extract categorical attributes by using cat encoder, which was extracted from data processor pipeline name transform cat. So this is the reason why if you name a categorical variable and you know the pipeline, and you know from that you can extract these features, transform features, by using this cat encoder dot get features name out. Once that is done, I created a data frame here, and then I'm displaying it down here. As you can see, this is the final output after we did this housing too. And then this one is actually, this includes response variable, but this one does not, because we entered we dropped median house value and then did the same processing. So both of them yield similar result, because when we are doing this one, we are specifying what columns we are going to apply. Remember, this one does not have household median house value, and this one also does not have. So in a way, we already dropped the features that are not in here. Now we are going to split our training and test data using our well-known train test split, and here I computed x and y and then split. Then to create a prepared data set, all I have to do is x train dot prepared, and then we can apply the data processor pipeline and get x, and give x train, and we can get x develop prepare by submitting x dev. So now I think this is all good. We are able to get the attributes. One of the important thing when you are doing your own data set is actually trying to compute these columns for the prepared data set. The reason why it is difficult or challenging is because we have to manually create these column names. Otherwise, because we are operating on numpy arrays, the output from the transformers doesn't have columns, so we have to externally compute them and then append to create a data set. That is, I found it somewhat like tedious, but for now we have to go through this process. Let's explore various models For first, before exploring other models, we can just look at how to apply on this one, on linear regression. So you have a prepared data set that we are fitting. It's a numpy array and then white array. So and then uh, there's a this is the prepared data set for development, xdev, and then I'm applying predictions on this particular numpy array. So we get a dev prediction. So you can compute RMSE here, which is what I'm printing here. Although RMSE is important, there are other measures. So I wrote a simple function so that you can give x data, y data, x test and y test, and also the model, a model, and then this model will try to compute, do the prediction on this x test. It compares against y test and print various metrics. So the important metrics here is root mean square, and because since squared is false, it is a root. So RMSE, if you take it out, it will become MSE. So MAE is mean absolute value, and then this is R square. It helps you understand how much it is explaining. And then you have the model type. So for example, when I try to print, I gave an input of linear regression, decision regression tree, random forest with various parameters, like here I gave an estimator as 100, and also support vector regression. So all I have to do is, if I call this function, it will print these values. You can see that our random forest regressor has better R square compared to other ones. Let's look at if you want to fine tune, like random regressor is doing good. So if you want to fine tune this particular model, you can use a grid search. So grid search is, first you have to specify the parameters that you want to explore. So look at the search space. So n estimator, it's a combination of these 3 values for estimator, 3 values for features, and then 4 values for depth. So using all of this one, it will iterate through all of these combination 3 times 3 times 4, right? 9 times 4, 36, and then you are going to get. So grid search we will set up grid search using this, where we have to give an estimator, which is a random forest regressor. I did not give other values here, so it will take this as the given value, and it will score all of this. Once it is scored, once you fit this one, it will evaluate all of the training data set using all these parameters, and it finds the best. You can print the best, and it says that the best is when max depth is 10, max features is 8. Looks like it went all the way up. Maybe there is some room to improve here. And number of estimators is 50. When we look at R square, it shows 0.79, which is actually lower than what we found here, 0.808. But maybe if I change the depth of these values, it might actually find better score than this, but for now this is the best among the available ones. So the best score is printed here. Feature importance, obviously the feature importance here, the attributes we calculated before by combining all the attributes for numerical, categorical values, and then we are looking at the importance here, and based on the results we can see that the median income is important in estimating median average value. More income, better house. So it's obvious, but the model also says the same thing. Ocean proximity, the closer, we don't know the direction, whether value goes up or down. I think inland means it's away from the beach, so it might actually be lower, but it doesn't show the coefficients here. So finally, if you want to productize, so that when you get a new data set, you want to apply this pipeline on that new data set and do the predictions. Yeah, we would be interested in prediction at that time. So we have seen data processor, and we know that the random forest regression with these parameters are important. So we can create a pipeline with these values. Once the pipeline is created, now if I want to estimate or predict for on y, for example, y development or x development. We can now save this. We can fit and then save. In fact, I think this code should be before saving the. So we can fit the model and then save it, save as a pickle file for future use, and you can upload it. Then once the model is available, you can essentially do dot predict and then you give the xdev. In fact, it should be, yeah, xdev, because it actually does data processing within this particular model. We don't have to transform it. Internally the data transform will take care of it. Then finally we'll get y prediction, which we can use it to compare against our y dev and compute our metrics. Yeah, I think that's pretty much it. This concludes this project, and what we can, I'll show the outline here. The configurations were mostly about setting up the data set and imports and so on, and we got the data from URL. So this is something you can actually try to understand how to get a data from a given URL in the form of TZ. And then we looked at the data properties, how different variables are, what the distribution of different variables and how much data is missing, and also looked at latitude and longitude in terms of understanding the blocks sizes and so on. And we did some feature engineering, and then understood what are the numerical and categorical features. We did some plotting, and then we created a new features and looked at correlation against our median house value. And pipeline building was something new, so this project actually helped me in particular to understand how to the nuances of developing a pipeline or transformers. The important takeaway for me was the numerical transformers mostly work on NumPy arrays, whereas I mean, whereas we are often used to give pandas data frame as an input. So what this does is that we have to explicitly remember the column names. We finally split the data into train and test, and then we explored various models, and we found out that random forest regression was the best. So we used those parameters after doing grid search. We plotted the feature importance and finally productize the final model so that we can load and do the prediction and a newer data set. So that concludes this particular project.